Hello everyone, welcome back to my channel, Ma'am Balot's Math Tutorial. Today we will be discussing all about combinations. Let us recall what is a permutation. So it is any arrangement of objects where order is important. And we have to take note that order really matters in a permutation. So the permutation of n distinct objects taken r at a time can be solved by p of nr is equal to n factorial over n minus r factorial when r is less than n. But the permutation of n distinct objects taken all at a time is equal to p of n and n is equal to n factorial. Now, what is a combination? So, what's the difference between a permutation and a combination? So, a combination is also an arrangement of objects, but it is without regard to order. So, take note that in combination, the order doesn't matter. Let us have example number 1. In how many ways can you arrange 3 letters from the word red? So observe here that we have 4 letters and we will be taking only 3 of them. So if we compute using the formula of the permutations, we arrive a value of 24, which means we have 24 different arrangements, which is shown here. Now if we focus on these different arrangements, observe that this group here have the same letters, only they have different orders. So in combination, this different arrangement can be considered only as one combination. Same goes for the second column. So they have the same letter but with different arrangement. Same with the third column and the last column. So therefore, if we take 3 letters from the word red, we have only 4 combinations. So that's the difference between the permutation and the combination. Let's have another example. Identify each situation if the order is important. So in this activity, we can identify what concept will we use in a certain situation, whether we will use the permutation or the combination, by just identifying if the order is important. Number 1, opening a combination lock. Is the order important in this situation? Yes, of course, the order is important because you cannot open a lock if the digits or the password you entered is in incorrect order. Example 2, choosing 5 questions to answer out of 10 questions. Is the order important? No. So the order is not important here because if you answer first number 1, then 2, 3, 4, 5, or you answer start from 5, then 4, 3, 2, 1, so still you answer the same numbers. Example 3, winning in a contest. Is the order important? Yes, of course, the order is important because if you win the first place, then another one must be in the second place. And if you are placed at the second place, then it would be in another order. Sample number 4. Entering the PIN of your ATM card. Is the order important? Of course, the order is important because you cannot access to your account if your PIN is in incorrect order. Number 5. Selecting 3 students for a committee. Is the order important? No, it's not. It is not important because the priority here is just to select 3 students, whether the first student is chosen, second or third, or he first choose the third student, then the second, then the first. Number 6, listing the elements in a subset. Is the order important? It's not. So the order is not important also in this situation because when you list the elements, it can be in different order as long as all the elements are there. So how do we compute the number of combinations in a certain situation? So we have the formula of C of n taken r at a time is equal to n factorial over r factorial times n minus r factorial, where your r here is less than n. But if you take n all at a time, the combination of n taken n is equal to 1. Because of course, we have only one combination to all of the objects that you need to combine. Let's have another example. In how many ways can a committee consist of 4 members be formed from 8 people? So in this case, our n is 8 because we will be choosing from 8 people, and r is equal to 4 because we will be taking only 4 of them. So from this given, we will now use the formula of the combination. So we have combination of 8 taken 4 is equal to 8 factorial divided by 4 factorial times 8 minus 4 factorial. Subtracting 8 minus 4, we've got 4 factorial. Then expanding the factorials, we have now 8 times 7 times 6 times 5 up until only to 4 factorial. And in the denominator, the other 4 factorial is expanded and the other one is remained, so that we can cancel out the 4 factorial in the numerator. And then observe that in the denominator, we have 3 times 2 times 1, which is equal to 6. So we can cancel out number 6 in the numerator from there. And also observe that 4 can be cancelled out from 8. So what's left in 8 is 2. So multiplying now what's left in the numerator, which are 2 times 7 times 5, so we have 70. So we have 70 ways. We have 70 number of combinations. Another example. If there are 10 teams in a volleyball tournament and each team must play every other team in the eliminations, how many elimination games will there be? So in here, n is equal to 10, and since in every game we have 2 teams which are playing, so r is equal to 2, since we will be computing the number of elimination games. So from that data, use now the formula of the combination. So we have the combination of 10 taken 2 at a time. So we have 10 factorial divided by 2 factorial times 10 minus 2 factorial. Subtracting 10 minus 2, so we have 8 factorial. Then expanding the factorials, we have now 10 times 9 times 8 factorial only because we have an 8 factorial in the denominator. And then the 2 factorial in the denominator is expanded. Now we can cancel out both 8 factorial in the numerator and in the denominator. And 2 in the denominator also can be cancelled out from 10. So what's left from 10 is 5. So what's left in the numerator is 5 times 9, which is equal to 45. So there will be 45 elimination games out of 10 teams. Example number 5. How many polygons can be possibly formed from 6 distinct points on a plane, of which no 3 of them are collinear? So in this situation, we will be having different cases since we are talking of different kinds of polygons. So we have case 1, if we will be focusing on the triangle, so therefore, if we have n which is 6, since we have 6 distinct points, then to form a triangle, we need only 3 points. That is why our r is equal to 3. In case 2, if we are aiming for a quadrilateral, then from n is equal to 6, we have r is equal to 4, since we need 4 points to form a quadrilateral. And then for case 3, we have a pentagon. So therefore, for n is equal to 6, we need 5 points to form a pentagon. And for case number 4, if we have a hexagon, so from n is equal to 6, we need also 6 points. So r is equal to 6 also. So we will now focus first in solving case 1, which is the number of triangles. So n is equal to 6 and r is equal to 3. So using now the formula of the combination, we have combination of 6 taken 3 is equal to 6 factorial divided by 3 factorial times 6 minus 3 factorial. Subtracting 6 minus 3, we have 3 factorial. And then we expand 6 factorial in the numerator and the other 3 factorial in the denominator. So observe that 6 is expanded up only 3 factorial so that we can cancel out the other 3 factorial in the denominator. Then what's left in the denominator are 3 times 2 times 1, which is equal to 6. So we can cancel out also the 6 in the numerator through them. So what's left now is 5 times 4, which is equal to 20. Therefore, we have 20 triangles if we have 6 points. Let us have case number 2, which is the number of quadrilaterals. So n is equal to 6 and r is equal to 4. So using again the formula, we have the combination of 6 taken 4 is equal to 6 factorial divided by 4 factorial times 6 minus 4 factorial. Subtracting 6 minus 4, we have 2 factorial. Then expanding 6 factorial, we have 6 times 5 times 4 factorial only, so that we can cancel out the 4 factorial in the denominator. Then, what's left in the denominator is 2 times 1, which is equal to 2, which can be cancelled out from 6. So, what's left from 6 is 3. So, we have now 3 times 5, which is equal to 15. So, there will be 15 quadrilaterals can be formed from 6 distinct points. Now let's move on to case number 3, which are the number of pentagons. So n is equal to 6 and r is equal to 5. So using the formula again, we have the combination of 6 taken 5, which is equal to 6 factorial divided by 5 factorial times 6 minus 5 factorial. Subtracting 6 minus 5, we have 1 factorial. Then we expand the numerator, so we have 6 times 5 factorial. So we now cancel out 5 factorial also in the denominator. So what's left there is 6. So we can only form 6 kinds of pentagons from 6 different points. And lastly, case number 4 is the number of hexagons. So since n is 6 and r is equal to 6, so we will use the formula of combination n taken all at a time, which is equal to 1. So therefore, combination of 6 taken 6 is equal to 1. Now to solve the problem, we will let n be the total number of polygons. So n is equal now to the combination of 6 taken 3, which is the number of triangles, plus the combination of 6 taken 4, which is the number of quadrilaterals, plus the combination of 6 taken 5, which is the number of pentagons, plus combination of 6 taken 6, which is the number of the hexagon. So substituting the values that we had solved earlier, we have now triangles are 20, then plus 15 quadrilaterals, plus 6 pentagons, plus 1 hexagon. So overall, we have 42 kinds of polygons that can be made from the 6 distinct points. Now it's your turn to answer your activity learning sheets. I hope you learned something from what we had discussed today. But please don't forget to like and subscribe. Thank you so much for watching. At your service, Ma'am Balot.